Hello, physics people. This is Physics Chapter 11, Lecture 2. This will be the final lecture for Chapter 11. In the book, open up to page 368. And in your notes, we're at the top of page 4. There's a few things I want you to follow along in your notes. A lot of bullet points to go over. And you can read the chapter and really learn all of this. But speed of light in the air is 3 times 10 to the 8th meters a second. You need to memorize that. For the speed of light, the denser the medium, the slower that light travels. Okay, that's a concept you're going to want to remember. The denser the medium, the slower light travels. So I put together a table here to show you that light travels in a vacuum, so no molecules, no particles whatsoever, 90,000 meters a second than in air. Now it still rounds up to 3 times 10 to the 8th meters a second, so that's what we use. But 90,000 meters a second is really a big difference between, not relatively because the number is so big, but 90,000 meters a second is pretty fast. So that just shows you that light travels slower as the medium gets more dense. And in water, you can see it's 25% slower in water than in air. All right, so in your book, it talks about Young's double slit experiment. So you're going to want to read through that, and I will post a video in the description box for you to watch about Young's double slit experiment. Go ahead and read through that. But that kind of shows how light tends to act as a wave. All right, that's what the double slit experiment did. So light as a wave. Constructive interference occurs when the crests and troughs of a wave overlap and make larger crests and troughs. I'll link you a video for that. Destructive interference when the waves, when the troughs and the crests cancel each other out. Okay, so that's called destructive interference. Again, watch the videos that I link in the description box. And we've got some of the things that you learned in chemistry on page 370 of your book, the electromagnetic spectrum. I will show you a video. I will link a video on that. So that's all of the light that comes from the sun, from the lowest energy radio waves to the highest energy gamma rays. And then you've got the visible spectrum. This is what you learned in chemistry, the Roy G. Biv acronym, red, orange, yellow, green, blue, indigo, violet. All right, so that's just what our eyes are tuned in to see. All right, again, you'll have videos to watch on that. The visible spectrum is between 400 and 700 nanometers, and a nano means 10 to the minus 9. You're going to have to memorize that. So let's just, the things that you're going to have to remember for working these problems is the speed of light. We call that c, is 3 times 10 to the 8th meters per second. That 1 nanometer is 10 to the minus 9 meters. Okay, that's something that you're going to have to remember as well. And when we're dealing with light, okay, just frequency then is going to be the speed of light over the wavelength, where in the last lecture it was the speed of sound. C is the speed of light. All right, let's work a few of these problems. So we're going to work 11.7 on page 372. So you definitely want to read the chapter. That's more important in this chapter than other chapters. There's just a lot of vocabulary. 11.7 says a recently developed laser using the treatment of skin disorders produces light with a wavelength of 578 nanometers. According to figure 11.10, what color is this light? All right, well, we would just flip back one page and see that 578 nanometers falls in the yellow spectrum. All right, and what is the light's frequency? Okay, so we'll do the math on that. So the color is yellow, and it asks for the frequency. Well, frequency is going to be the speed of light, 3 times 10 to the 8th, divided by the wavelength. And it says that the wavelength is 578 nanometers, so you just need to do 578 times 10 to the minus 9 meters. We have to change it to meters. Your calculator will move the decimal 2 places to the left automatically and do 5.78 times 10 to the minus 7, but you don't have to do that. Type it in like this, 578, and then hit that double E button. You hit the double E button, and then minus 9, and it will change it to times 10 to the minus 7 for you. All right, so when you place that into the old calculator, you will get 5.19 times 10 to the 14th hertz. All right, underneath 11.7 is 11.8. That one says, as shown in figure 11.9, waves used to send radio signals are electromagnetic waves. I often listen to a radio station that transmits with a frequency of 1240 kilohertz. What is the wavelength of these waves? Well, we can figure out the wavelength by rearranging the frequency equation. Wavelength is going to be the speed of light over the frequency. So that's 3 times 10 to the 8th divided by the frequency. The radio station was 1240 kilohertz. All right, so we need to change that to hertz. So that's 1240 times 10 to the 3rd hertz. All right, so 1240 kilohertz would be 1,000 hertz. You can either add 3 zeros or just do times 10 to the 3rd. And that is 241.9 meters. All right, so the math is not very hard for the light as a wave section. Now let's look at light as a particle on page 5 of your notes. All right, so again, you can read through all this, but our equation, the main equation we're going to use is E, energy, is equal to HF, Planck's constant, times the frequency. So light as a particle, we are assuming that light is made up of tiny energy packets called photons. So again, I will be posting a video for you to watch, a short video to help explain this. Planck's constant you don't have to memorize. I will give that to you. The photoelectric effect is liberating electrons by shining light on a metal surface. I've got a video for that. I'll draw a little thing there. And the work function is the energy with which a metal holds on to its electrons. And then we also have the particle wave duality theory of light that we talk about, where light acts as both a particle, shown by the photoelectric effect, and a wave, right, shown by the double slit experiment. So light does both. All right, so we have, let's talk about the photoelectric effect for just a second. All right, you do need to read this section in the book, but let's say you have a metal and you were to shine light on that metal. If the light has adequate energy, then electrons from the surface of the metal will bounce off. They will be what we call liberated from the metal. All right, that shows that light is acting like a particle, but the light has to have enough energy, and the amount of energy that that light needs is called the work function. Every metal has a different work function. So if light is greater than the work function, then electrons will be liberated, and the amount of energy they will carry with them is the difference between the light and the work function of the metal. If light is less than work function, so the energy, we're talking about energy, then electrons are not liberated. Okay, so I have a good video that shows a experimental setup to show the photoelectric effect. All right, so let's take a look at the math for light as a particle. All right, the main equation is E is equal to hf. All right, you have to memorize that equation, but Planck's constant you don't have to memorize. That's 4.14 times 10 to the minus 15 electrovolt seconds. Okay, so in chemistry we used a different unit, so we had a different value than 4.4 times 10 to the minus 15, but light has such a low energy per photon that we needed to use a smaller unit. All right, so, and of course energy for E and frequency. So let's take a look at 11.9, and we are right at the end of our chapter 11 here, so 11.9 on page 376. All right, so that says cesium has a work function of 2.14 electrovolts. If green light with a wavelength of 501 nanometers shines on cesium, what's the maximum kinetic energy that the electrons will have as they leave the metal? All right, well, first of all, we need to get the energy of the light that is green, the 501 nanometer light. All right, so energy is equal to Planck's constant times the frequency. We know that frequency is equal to the speed of light over the wavelength, so that's 3 times 10 to the 8th divided by 501 times 10 to the minus 9 meters. Remember, we have to take nanometers and change it to meters. So the frequency is 5.99 times 10 to the 14th hertz. So now we can get the energy of the green light. That's going to be 4.14 times 10 to the minus 15 times 5.99 times 10 to the 14. All right, so that energy is 2.48 electrovolts. Now the work function, the maximum kinetic energy that those electrons would have is the work function, the energy of the light minus the work function of the metal. Okay, the energy has to be greater than the work function, and that's measurable, as you'll see in the video that you watched. So the energy of the light is 2.48. The work function of cesium is 2.14. Right, so you would, if you measured with a meter the energy of the electrons that are bouncing off the metal, they would have up to 0.34 electrovolts of energy. All right, let's do 11.10. So 11.10 says a metal emits electrons when illuminated with light. However, if the light wavelength is greater than 195 nanometers, no electrons are emitted. What is the work function of the metal? All right, so the work function is the energy that occurs at 195 nanometers. Okay, so the energy equation involves frequency. Okay, so we need to get the frequency. It's the speed of light over the wavelength, 3 times 10 to the 8th divided by 195 times 10 to the minus 9. Right, and that is 1.54 times 10 to the 15th hertz. Now we can get the energy. So that's 4.14 times 10 to the minus 15th electrovolt seconds times 1.54 times 10 to the 15th hertz. All right, and that is 6.37 electrovolts. All right, so that is the work function, or the amount of energy that your light needs to have to liberate electrons. Okay, so that finishes up chapter 11. Right, so the homework that goes with this lecture is you can do review questions, page 383. You can do 5 through 10, so finish those up. Practice problems, page 384. You can do 7 through 10. Just a few points before I shut off the video here. You really need to read this chapter, including the last page about James Clerk Maxwell and Albert Einstein. Everything is fair game on this test, okay? So read chapter 11, very important. And also, to help you understand these concepts better, watch the videos that I link in the description box. All right, that's really going to help you understand a lot of these concepts about the double slit experiment, about the photoelectric effect, etc. All right, so that does it for chapter 11, and I will talk to you next video.